Hey everybody. So we're going to do another example of taking the derivative of a vector function. So right now we're just looking at a picture. The function r of t is equal to the cosine of t, sine of t, and t. Those are the three component functions as I've written here. We've seen this one before. It's a spiral, right, wrapped around the z-axis, right? In the x and y components, we've traced out a circle, except as they're tracing out the circle, the z component is changing. So we get this nice corkscrew. Okay, so let's look at a few things. We have first, let's look at the vector function itself. This is this vector, remember, that points along this curve, right? So the curve itself is not the vector function. The vector function is pointing at different points on the curve given a different value of t. And so let's take its derivative, right? So what we saw in previous videos, the derivative of vector functions is a fairly simple process. R prime of t is going to be equal to, we just take the derivative of each component function. The derivative of cosine is negative sine of t. The derivative of sine of t is cosine of t. And the derivative of t is 1. Okay? So now, this is a new vector function, right? So this now is equivalent to when we took derivatives when you first learn about derivatives, you take derivatives at a point and you take derivatives as a function. This is our derivative as a function, right? So this is spitting out, right, for each value of our parameter, right? That red arrow is the vector at that point. Right, so if you choose any point on this curve and you put in t, right? So if you choose any t, r of t spits out a vector that points at a point on the curve. R prime of t spits out a vector that is tangent to the curve at that point. So one of the things we also said last time is that we defined the tangent line to a curve. Actually, before we do that, let's take one more view of this thing. If we look straight down, we get this nice visualization. You can see the tangent vector, right? It's just pointing exactly how we imagine the tangent to in that direction. Okay. Oops, let's get it back into our. There we go. Okay. So there is our curve. Maybe I'm going to remove the axes. Let's try it like that for a bit. Okay, so now let's define the tangent line at r of t naught. So t naught is some value of t. Then the tangent line, I'll call it I'll give it a different parameter, L of S. Actually, let's use lambda. We don't use lambda enough anymore. Sometimes people use lambda, another Greek letter, as the parameter of this, the variable in this vector function. And so what we would do to create the tangent line, we start with the vector r of t naught. So that's like picking a particular point on this curve. And then you add lambda times the vector r prime of t naught, right? So what is this going to do? Well, r of t naught is the green vector, and then we're adding to it a scaled version of this red vector. So we'll get a vector here, right? And if we scale it again, we'll get a vector out here. And so as we scale that vector, we get a vector that points at all the vectors on our tangent line. And what it will look like is that, right? So there is the tangent line to that curve, right? So again, I've kept everything as a function. So if I move to a different points, it shows me a different tangent line. I could look from above again. Looking down the z-axis, we see these tangent lines that are exactly as we imagine them to be in this perspective, but they're also tangent when we take that z-coordinate into account. All right, maybe I'll put my axes, let's just do this. There we go. Let's forget about that. Okay, so there's our vector function. I want to notice one other thing about this particular vector and its vector function and its derivative. Notice some of the other ones we've looked at as we move around the curve, that tangent vector changes size. That's what we've seen previously. This one doesn't appear to be, right? And we haven't gone into the details of this yet, but we will find out if we're thinking of a particle traveling along this curve with a parametric equation, you know, built with the same component functions as our vector function, this tangent vector will represent the velocity. Well, if this tangent vector is not changing size, it means the velocity is not changing size. Let's verify this instead of just going by how it looks by computing the magnitude of r prime of t. All right. Well, the magnitude of r prime of t is the square root of, we take each component and square it, so sine squared t, oops, sorry, I have that negative, so I can't do that. We're going to have negative sine squared, I did it again. I want the squared out there. Arg. All right, sine of t squared plus cosine of t squared plus 1 squared. But of course, when we square the negative, which is why it was so important to write that correctly, I get sine squared t plus cosine squared t plus 1. And this sine squared plus cosine squared is 1. So I get that it doesn't matter which point I'm at along my curve, the tangent vector is always going to be the square root of 2. Magnitude of the tangent vector is always going to be the square root of 2, right? So that's not always the case, right? Other vectors, depending on which point you evaluate at, you get different magnitudes for your tangent vector. But in some cases, and this is one of them, if we had a particle traveling by these component functions, right, with parametric equations equivalent to these component functions, it would be traveling at a constant speed, okay? Okay, that is everything I want to say about this example. Thanks, everybody. I will see you in the next one.